Hello, my name is Aizere Issaliyeva. My student number is 230 20 88 and 23. My topic is malware detection using kernel behavior analysis. Why kernel behavior detection? So let me start with the motivation. Modern malware doesn't look obviously evil anymore. Binaries are packed, sophisticated, and constantly changing, so classic file scanning and simply user space monitoring are easy to evade. But no matter how much malware hides its code, it still has to talk to the kernel, to open files, create processes, use the network, and so on. If we observe this kernel-level behavior, we see what the program is really doing, not just how the binary looks. The long-term goal is near real-time, robust malware detection or normal commodity systems. Problem statement. Formally, we can describe the problem like this. We observe a stream of kernel events produced by running programs. For each unit of execution, for example, process, a user session, or a fixed time window, we want to decide, does this look malicious? At the same time, the detector has to run online with low latency and small CPU and memory overhead. Otherwise, nobody will deploy it in a real system. Threat model. Now a few words about the threat model. We assume that attackers are reasonably strong. They can pack and obfuscate their binaries, inject code into trusted processes, and imitate normal behavior to blend in. Our detector should run with minimum privilege, ideally as a super space agent that uses official IPs. It also needs to stay stable across OS versions and hardware. Fully privileged kernel rootkits are considered out of enforcement scope. They can still hide their events, but their existence strongly influences how we design and evaluate our sensors. Kernel telemetry signals. Kernel behavior analysis relies on several big families of signals. First, system call sequences and arguments. Secondly, object and handle operations, so files, sockets, registry objects, and processes. Thirdly, shadow and I/O activity, context switches, disk and network traffic. And finally, memory and image events, page faults, mappings, model loads, all platforms, Windows, Linux, macOS, iOS, and Android, expose some version of these signals even though the IPs are different. System call traces. System calls are basically the IPs between application and the kernel. By looking at the ordered stream of calls from a process plus their arguments, we can see which resources it touches. File path, access modes, flags, socket addresses, and so on. These traces can be modeled as n-grabs or Markov chains, or just as time-stamped sequences for deep models. Typically, patterns will help us separate normal workflows like a browser from a malware, for example, ransomware that suddenly starts encrypting lots of files. Object and handle activity. On top of raw calls, we can look at the high level of objects that includes files and directories, register keys or config stores, network sockets, and also processes trees and load models. Certain patterns are clearly suspicious, strange or master or mass registry edits, repeated handle duplication into sensitive processes, or unexpected writes to system binaries, tracking how objects are opened, written, renamed, and closed. Give us a behavioral view that is harder for attackers to fake consistently. Scheduler and I/O telemetry. Another angle is the schedule and I/O behavior. Here we'll look at the context switches, CPU usage, disk reads and writes, and network connections with their frequency and ports. Ratios of CPU to I/O and how bursty the activity is help separate interactive workloads from automated malware. For example, a user casually working in a Word has a very different pattern from a piece of malware that rapidly scans the file system or exfiltrates data. Memory and model events. Memory and image events are especially useful for stealthy malware. We can monitor page faults, new memory mappings, loading and unloading of executables and DLLs, and the creation of writable and executable memory regions. These patterns are typically for unpacking in memory, shellcode injection, or fileless malware that never drops a payload to disk. Combined with other sensors, they help us catch more advanced attacks. Platform IPs for kernel telemetry. Different operating systems expose their telemetry to different IPs. On Windows, we have ETW and kernel callbacks. On Linux, we use eBPF with key probes, trace points, and LSM hooks. On macOS and iOS, we're the endpoint security framework. On Android, we can trace binder IPC plus kernel audit events. The nice thing is that all of these give us fine-grained time spent events without having to ship custom kernels. Windows telemetry, ATW, and callbacks. Focusing on Windows ATW has providers for processes and read lifecycle, image loads, file and registry access. Kernel callbacks complement this with hooks for process creation, handle operations, and registry changes. Together they form a very rich stream of behavioral data, which is great for sequence modeling. The trade-off is what HCW usually requires admin rights, and we need careful buffering so we don't lose events under heavy loads. Linux telemetry, eBPF, and LSM. On Linux, extended BPF has become the main tool. Small eBPF programs attached to kernel functions or trace points store state in maps and send events to user space via ring buffers. LSM hooks additionally let us enforce security policies on sensitive operations file like network and access. The benefits are flexibility and low overhead on stock kernels, but we have to deal with the kernel version drift, strict verified limits, and we must cap event rates to keep the system stable. macOS and iOS telemetry, endpoint security. On Apple platform, we use the endpoint security framework. It delivers structured events for processes execution and exit, file opens and writes, and memory mapping and protection change. The monitoring logic runs a user space agent with a special code sign-in entitlements, and endpoint security replaces older CAUF interfaces. The main engineering challenge is back pressure. We need good buffering so the agent doesn't drop the important events when the system is busy. So, Android telemetry binder IPC. Android has its own flavor of telemetry. Binder is the core IPC mechanism for communication between apps and system services. By tracing binder calls and combining them with the kernel transpoints and eBPF, we can see the processes and trees lifecycle, file and network activity, and which system services are being used. This way we can analyze app behavior at the OS boundary without modifying the Android kernel.